Hello everyone. So this project is about time series applications on big data. The dataset that we have used in it is number of aircrafts departing in Italy. And for the project, I have used the number of aircrafts departure in Italy from 1948 to 2014. The data has been collected from the Institute Nazionale di Statistica. It's the National Institute of Statistics in Italy, ISTAT. So we will begin the process by checking if our dataset that we are using has a plot of stationarity, if there is stationary, or and its variance, it has a high variance or low variance. If it is found to be non-stationary, the transformations are applied to achieve the stationarity. Subsequently, model selection is being performed using the ACF and PCF plots, along with information criteria such as AIC, BIC, and HQC. The most suitable model are constructed, and their residues are being checked if there are white noise. If it is the residues are the realization of the white noise. If they are the realization of the white noise, so they are Gaussian white noise or not. In the final stage, the test set, because the data will be split into test and train, so in the test set we will be used to check the model. The model with the less root mean square error will be selected as the best performing model, and this model will be used to forecast the future values with enhanced accuracy. All the analysis is being computed using the application Gradle, ensuring robust and reliable results. So we will start with the preliminary analysis. As you can see, the plot, it shows an increasing trend of the number of aircraft departures in Italy from 1948 to 2014, which means that it is not stationary. So to make it stationary, we need to do data transformation. For the data transformation, we will do the first difference. The first difference is you need to apply the lag operator for that. After having the first difference, this is the result that we have. To access the stationarity, we did the ADF test. Is the augmented Dickey-Fuller test. This was conducted using the Python, and the result says that the statistics shows that the ADF test result is negative, and it exceeds the critical value of minus 3.5, which is the lowest one, and it is lower than that as well. Additionally, the p-value is less than 0.05, and allowing us to reject the null hypothesis of non-stationarity. So this means that the graph is stationary. But where the problem is, we can see that there is high variance. The standard deviation is of 19,297. So we need to reduce the variance. For that, we will first apply the log operator to our original dataset and then find the first difference. And now we can see the standard deviation is near to 0. And the ADF test value is again more negative than the lowest value of the critical. And the p-value is less than 0.05, which shows that the graph is stationary and has less variance. So for the next step, we break our dataset. So our original dataset was from 1948 till 2014. We break 1948 till 2000 with the 53 observations for the training set, and while the test set consists of 2001 till 2014 for the 14 observations. So for the training set, we applied the correlogram and check the results. We check that the second leg is out of the significance level of 0.05. So we conducted that. That the process is AR of order 2. This means that it is of ARIMA 210, because 2 is the AR autoregressive model, 1 is the first difference that we had, and 0 means the moving average. Next, we have the information criteria, in which AIC, BIC3, and HQC. When we on Gradle, there is an RMax function we applied on it. We set the maximum AR value to 5, maximum MF value to 5, and checked the results. We found out that the best model was with P2 and Q1, which was the lowest amongst the all. For the AIC, the lowest was 2.1 model. For the BIC, again the lowest one for 2.1 model, and HQC again 2.1 model. So we select that model. If it is ARMA of 2.1, this means ARIMA 2.11. Now we will check these two models on if their residues are a realization of white noise or not. So we check the residues, we check the plots of the residues, the correlogram, and their all legs are within the significance level. So we can conclude that it is a realization of white noise. Now we need to check if it is a realization of the Gaussian white noise. We will check the histogram and the QQ plot. So the p-value of the histogram is 0.0175, which is less than 0.05. So the residual does not follow the Gaussian distribution. And you can also see from the QQ plot, it is not fitting with the straight line. So it is not the Gaussian white noise, but it is the realization of the white noise, the ARIMA 210 model, this one. Now we'll check the second model, 211 model. This is just the coefficients that we find out from this model. And we figured out that when we check the residues of this model, so the residues are within the range of correlogram significance level. So this means that it is a realization of white noise. Now we need to check what is the Gaussian white noise. We check the histogram and the QQ plot. So for the histogram, we check the p-value is 0.0665, which is greater than the significance level of 0.05. Hence, we accept the null hypothesis, meaning that there is a strong evidence against the assumption that the residual follow the Gaussian distribution. So hence, it is Gaussian white noise. This is also confirmed with the QQ plot, as a lot of points are in line with the line. Now, we will check the forecast on test set. We can see that there are two values. So our test set, as I told you, test set was from 2001 to 2014. So we can see that there are two values. 2013, 2014 values does not fit in with our forecast range for the ARIMA 210 model, and the root mean square error was registered at 0.56. And for 211, the two values of 2000, and if I closely tell you, the 2013 it was something this. It was close to the forecast, but not. It is close to the forecast as compared to the previous ARIMA 210 model, which was less close to the forecast. So, and it has a root mean square value less than the previous model as well, which was 0.56, but here it is 0.5. Now the problem is this root mean square value is of the logarithm, but we need for the actual data set. So for the actual x of t, we need to find the exponential of zt. For that, I used an Excel. So in this, what I did was I calculated the yt, the predicted yt, the error, and respectively the exponent parts. And with the exponent part, I calculated the actual root mean square error of the xt. Similarly for ARIMA 210 and ARIMA 211. And I compared the both of those models, and the minimum root mean square was of ARIMA 211. So this is being selected as a best model, and we will use it for the forecast of the future values. And for the future values, I used the 20 future value prediction from 2015 to 2034, and this is the result that we got. So for the future forecast, indicate the number of aircraft departure in Italy is expected to increase after 2014. We can see after 2014 it is an increase, and the trend is increasing. However, this prediction does not account for exogenous factors that might influence the trend. For instance, while the forecast suggests a linear growth, real-world events such as the COVID-19 pandemic that happened in 2019 led to a drastic reduction in the aircraft departures. Other factors may significantly impact this trend, include weather, climatic conditions, changes in aviation regulation, international relations, shift in political mobility, and most importantly, geopolitical conflicts and security issues, which might hinder this graph. So therefore, this is important to recognize that the growth trajectory will not continue indefinitely and is subject to substantial variability.